Picture yourself at the edge of everything we know. Far beyond Neptune's blue storms, a cosmic wilderness stretches into the darkness of space. This is where our solar system holds its deepest secrets, in a realm we call the Kuiper Belt. Out here, countless frozen worlds drift silently through the void, each one a time capsule from the dawn of our cosmic neighborhood. These ancient bodies have witnessed the birth of our planets, preserving stories from a time when our solar system was young. You might think this sounds like something from a science fiction movie, but this mysterious band of ice and rock is very real, circling our sun like a vast celestial ring. It's a place where temperatures plunge to near absolute zero, where sunlight is just a distant whisper, and where objects as large as planets lurk in the eternal twilight. Welcome to a journey to the outer reaches of our cosmic backyard. Here, in the depths of space where past meets present, we're about to explore one of the most fascinating frontiers in modern astronomy. What if I told you that right in our cosmic backyard, there exists a vast territory that remained virtually unexplored until the late 20th century? A place so remote yet so significant that it completely changed our understanding of our solar system. In this distant realm, we've discovered objects as large as planets, challenging everything we thought we knew about what makes a planet a planet. Some of these worlds have their own moons, complex atmospheres, and possibly even hidden oceans beneath their frozen surfaces. The Kuiper Belt isn't just another region of space. It's a cosmic time machine, preserving the pristine conditions from the earliest days of our solar system. Like a frozen museum orbiting our sun, it holds clues to our own origins and the grand story of how our planetary neighborhood came to be. If this cosmic journey through the frozen frontiers of our solar system has sparked your curiosity, don't forget to hit that like button. And to continue exploring the mysteries of space with us, subscribe to Exploring the Universe. Together, we'll venture beyond the known and uncover the secrets of our cosmic home. The story of the Kuiper Belt begins not with telescopes, but with mathematics and human intuition. In 1951, Dutch-American astronomer Gerard Kuiper proposed something revolutionary: the existence of a vast disk of icy bodies beyond Neptune's orbit. While he wasn't entirely correct in his specific predictions, his work laid the foundation for one of astronomy's greatest discoveries. Interestingly, Kuiper wasn't the first to suggest such a region. In 1943, Kenneth Edgeworth had already proposed a similar idea. This is why you might sometimes hear people refer to it as the Edgeworth-Kuiper Belt. But it was Kuiper's detailed theoretical work that caught the attention of the scientific community. For decades, this remained purely theoretical. Astronomers searched the outer solar system, but the objects they were looking for were simply too dim, too distant, and too slow-moving for the technology of the time. It wasn't until 1992 that everything changed. On August 30th, 1992, astronomers David Jewitt and Jane Liu made a discovery that would revolutionize our understanding of the solar system. Using the University of Hawaii's telescope at Mauna Kea, they detected an object moving slowly against the background stars. This object, later named 1992 QB1, was the first confirmed Kuiper Belt object after Pluto and its moon Charon. This discovery opened the floodgates. Within just a few years, astronomers had found hundreds of similar objects. Today, we know of over 2,000 Kuiper Belt objects, and astronomers estimate there could be hundreds of thousands more waiting to be discovered. The impact of this discovery was profound. Our entire model of the solar system had to be rewritten. We went from seeing our cosmic neighborhood as a neat, orderly system of 9 planets to understanding it as a complex, dynamic environment with multiple regions and populations of objects. This new understanding forced us to reconsider what we thought we knew about planetary formation and evolution. It helped explain the origin of short-period comets and provided new insights into the early history of our solar system. Perhaps most famously, it led to the reclassification of Pluto in 2006. We realized that Pluto wasn't a unique 9th planet, but rather the first discovered member of an entirely new class of solar system objects. The discovery of the Kuiper Belt also highlighted how much we still had to learn about our own cosmic backyard. Here was an entire region of the solar system, containing countless worlds, that had gone undetected for most of human history. It raised an intriguing question: what else might be waiting to be discovered in the outer reaches of our solar system? Today, the study of the Kuiper Belt continues to yield new surprises. Each new discovery adds another piece to the puzzle of our solar system's history, helping us better understand not just where we are in space, but how we got here. What began as a theoretical prediction has become one of the most active and exciting fields in modern astronomy, reminding us that sometimes the greatest discoveries aren't in the farthest reaches of space, but right in our own cosmic neighborhood. Let's embark on a detailed exploration of this fascinating region of our solar system. The Kuiper Belt is truly vast, stretching across an enormous expanse of space that's difficult for the human mind to comprehend. To understand just how far away the Kuiper Belt is, let's put it in perspective. While Earth orbits at 1 astronomical unit from the Sun, approximately 93 million miles, the Kuiper Belt begins at around 30 astronomical units, right where Neptune orbits. From there, it extends outward to approximately 50 astronomical units from the Sun. That's over 4.6 billion miles from Earth at its closest point. To really grasp these distances, consider this. At these distances, sunlight is so weak that it takes over 4 hours for the sun's rays to reach the inner edge of the Kuiper Belt. At its outer regions, temperatures plummet to nearly minus 230 degrees Celsius, cold enough to freeze most gases into solid ice. The Kuiper Belt is a complex mixture of materials that tell the story of our solar system's formation. The objects found here are primarily composed of what astronomers call volatiles, substances that easily transform from solid to gas. The most abundant of these is water ice, but that's just the beginning. We find significant amounts of methane ice, giving many Kuiper Belt objects their reddish color when exposed to space radiation. There's also ammonia ice, carbon dioxide ice, and various organic compounds called tholins. These materials are mixed with rocky materials, silicates, and metals that were present in the original solar nebula. What makes this composition particularly interesting is that these materials are largely unchanged since the solar system's formation 4.6 billion years ago. The extreme cold has effectively preserved these primordial ingredients, making the Kuiper Belt a cosmic freezer storing samples from our solar system's birth. The population of the Kuiper Belt is remarkably diverse, ranging from tiny dust particles to worlds larger than our moon. Let's break this down by size categories. The smallest objects are cosmic dust and debris, measuring just micrometers across. Then we have objects ranging from boulder size up to about 100 kilometers in diameter. These make up the majority of the belt's population. Moving up the size scale, we find larger bodies known as classical Kuiper Belt objects, typically several hundred kilometers across. These orbit in relatively stable, circular paths. At the top of the size hierarchy are the dwarf planets. Pluto, the most famous resident, measures about 2,377 kilometers in diameter. We've also discovered other impressive worlds like Eris, Make, and Haumea. These larger objects often have their own moons, and some even possess atmospheres. The belt isn't uniformly distributed either. It contains several distinct populations: the classical objects in fairly circular orbits, the resonant objects like Pluto that orbit in harmony with Neptune, and the scattered objects in more elongated orbits. What's particularly fascinating is that astronomers estimate we've only discovered a small fraction of what's actually out there. Current models suggest there could be hundreds of thousands of objects larger than 100 kilometers in diameter and billions of smaller ones, making the Kuiper Belt a vast cosmic wilderness still waiting to be fully explored. In the dim twilight of this outer region, these objects move slowly through their orbits, taking hundreds of years to complete a single trip around the Sun. Each one is like a time capsule, preserving conditions from the early solar system, waiting to tell its story to those who venture to study it. Let's venture into one of the most fascinating aspects of the Kuiper Belt, its remarkable inhabitants. These distant worlds, each unique in its own way, have revolutionized our understanding of our solar system. Pluto, discovered in 1930, was our first glimpse into this mysterious region, though we didn't know it at the time. For 76 years, it held the title of our 9th planet, until a dramatic reclassification in 2006 that sparked worldwide debate about what defines a planet. But Pluto's demotion to dwarf planet status didn't diminish its importance. If anything, it elevated our understanding of its true nature. Thanks to NASA's New Horizons mission in 2015, we now know Pluto is far more complex than anyone imagined. It boasts a thin atmosphere that changes with its seasons. Its surface features vast plains of frozen nitrogen, mountains of water ice as tall as the Rockies, and a heart-shaped region called Sputnik Planitia that may hide a subsurface ocean. Pluto also hosts 5 moons, with Charon being so large that the two are considered a binary system. Eris, discovered in 2005, actually triggered the debate that led to Pluto's reclassification. Slightly more massive than Pluto but slightly smaller in volume, Eris has a highly elliptical orbit that takes it far beyond the main Kuiper Belt. Its surface is covered in frozen methane, giving it one of the brightest and most reflective surfaces in the solar system. Make, named after the creation deity of the Rapa Nui people, is another fascinating world. It's slightly smaller than Pluto and has a reddish tint due to the presence of complex organic compounds called tholins. Unlike its larger cousins, Make appears to lack a significant atmosphere, though it does have at least one known moon. Haumea stands out for its unusual shape. It's elongated like a rugby ball due to its rapid rotation. It spins so fast that it completes one rotation every 4 hours. This dwarf planet also boasts a system of rings, discovered in 2017, making it one of the most peculiar objects in the Kuiper Belt. It has 2 known moons and a surface composed almost entirely of crystalline water ice. Beyond these larger worlds, the Kuiper Belt hosts an incredible variety of objects. Plutinos. These objects, like Pluto, orbit in resonance with Neptune, completing 2 orbits for every 3 of Neptune's. This dance with Neptune helps keep their orbits stable over long periods. Binary systems. Many Kuiper Belt objects come in pairs, with some even forming triple or multiple systems. These partnerships provide valuable information about mass and density calculations. Centaurs. These objects cross between the orbits of the giant planets and may represent transitional objects between the Kuiper Belt and the inner solar system. The diversity extends to composition as well. While water ice is common, we find varying amounts of methane, nitrogen, and carbon monoxide ices. Some objects appear dark and reddish, while others are surprisingly bright. This variety in composition tells us about the conditions in different parts of the early solar system. Size distribution is equally fascinating. Current surveys suggest a power law distribution, meaning there are far more small objects than large ones. For every object 100 kilometers in diameter, there might be thousands of 1-kilometer objects. What makes these frozen worlds particularly intriguing is that each tells a different part of our solar system's story. Their orbits, compositions, and physical characteristics provide clues about the violent early days of planetary formation and the subsequent evolution of our cosmic neighborhood. Perhaps most excitingly, we've only scratched the surface. Many large objects likely remain undiscovered in the outer reaches of the belt, and each new discovery has the potential to reshape our understanding of this distant realm once again. Journey with us back in time, to when our solar system was nothing more than a swirling disk of gas and dust around our newly formed Sunday. The Kuiper Belt stands today as a living museum of this ancient era, preserving evidence of our cosmic origins in its frozen depths. The Kuiper Belt isn't just a collection of distant, frozen objects. It's a surviving remnant of the very disk that gave birth to our planets. About 4.6 billion years ago, our solar system began as a vast protoplanetary disk, rich with gas, dust, and ices. While most of this material eventually formed the planets we know today, the outer regions of our solar system tell a different story. In these distant reaches, where temperatures were eternally cold and gravitational interactions were weaker, much of the original material remained relatively undisturbed. The objects we find in the Kuiper Belt today are essentially cosmic time capsules, preserved by the extreme cold and isolation of deep space. What makes the Kuiper Belt objects so valuable to scientists is their pristine nature. Unlike the planets, which have undergone significant geological and atmospheric processing over billions of years, many Kuiper Belt objects remain largely unchanged since their formation. These objects contain some of the most primitive materials in our solar system. The ice crystals found on their surfaces maintain the same chemical signatures they had billions of years ago. The ratios of different isotopes in these ices tell us about the conditions present in the early solar system. Even the distribution of these objects in space provides crucial information about the gravitational forces that shaped our planetary neighborhood. The organic compounds found in these bodies are particularly intriguing. These complex carbon-based molecules might represent the same kind of materials that eventually led to life on Earth. By studying them, we gain insights into the chemical inventory available during our planet's formation. Perhaps one of the most revolutionary contributions of Kuiper Belt studies has been their role in understanding planetary migration. The current arrangement of our solar system wasn't always as we see it today. The study of Kuiper Belt objects led to the development of the Nice model, named after the city in France where it was first proposed, which suggests a dramatic restructuring of our solar system early in its history. According to this model, the giant planets formed much closer together than they are now. As they migrated to their current positions, their gravitational influence dramatically affected the Kuiper Belt. Jupiter's powerful gravity cleared vast regions of the solar system, forcing smaller bodies either inward or outward. Neptune's outward migration scattered countless objects, creating the scattered disk we observe today. Some objects were captured in orbital resonances, explaining the large number of Plutinos and other resonant objects. This migration theory helps explain several puzzling features of our solar system: the current orbits of the giant planets, the structure and composition of the asteroid belt, the late heavy bombardment period of Earth's history, the various populations within the Kuiper Belt itself. Understanding the Kuiper Belt's history has implications far beyond our solar system. As we discover more planetary systems around other stars, the lessons learned from our own solar system's evolution become invaluable. We can better predict the stability of other planetary systems. We gain insights into how common our solar system's architecture might be. We can better understand the conditions necessary for planetary formation. The Kuiper Belt continues to surprise us with new discoveries. Each object we study adds another piece to the puzzle of our cosmic origins. From the mysterious orbits of distant dwarf planets to the composition of the smallest KBOs, every observation helps us better understand the incredible story of our solar system's formation and evolution. In many ways, the Kuiper Belt serves as both a window to our past and a key to understanding our future in space. As we continue to explore this distant region, we're not just learning about a collection of icy worlds. We're uncovering the story of our own cosmic origins, written in ice and rock at the edges of our solar system. The exploration of the Kuiper Belt represents one of humanity's greatest technological achievements, pushing the boundaries of what we can accomplish in space exploration. The New Horizons mission stands as one of NASA's most ambitious ventures into deep space. Launched in 2006, this piano-sized spacecraft embarked on a nearly decade-long journey to reach Pluto, traveling at speeds of up to 36,373 miles per hour, the fastest spacecraft ever launched from Earth. On July 14, 2015, New Horizons made a historic achievement by completing the first-ever flyby of Pluto, unveiling a world of surprises. The images and data returned to Earth were revolutionary. Pluto's complex geology was revealed, showcasing mountains composed of water ice and expansive plains of frozen nitrogen. This was our first view of Pluto's thin atmosphere, showing its delicate interactions with the solar wind. Additionally, New Horizons captured detailed images of Pluto's 5 moons and found hints of possible subsurface oceans, expanding our understanding of what might lie beneath this distant dwarf planet. But New Horizons' journey didn't end there. In 2019, the probe accomplished yet another groundbreaking feat by reaching Eris, formerly known as Ultima Thule, the most distant object ever explored up close. This encounter provided unprecedented insights into the early solar system, especially regarding the formation of planetesimals, the building blocks of planets. Exploring the Kuiper Belt, however, is far from simple and pushes the boundaries of our technology. The extreme distances alone present significant obstacles, with signals taking hours to travel each way, limiting real-time communication and drastically reducing bandwidth. Solar power is weak at these distances, making nuclear power sources essential to mission success. Environmental factors add to the challenge, as temperatures approach absolute zero, -273 degrees Celsius, with light levels at merely 1/900th of what we receive on Earth. There is also the constant risk of collision with unseen debris, and with limited fuel reserves, any course corrections must be calculated meticulously. Technically, these missions demand highly sensitive instruments, extreme long-term reliability for spacecraft, navigation through poorly mapped space, and complex data management capabilities that allow for both storage and transmission across vast distances. The future of Kuiper Belt exploration holds thrilling possibilities, with several proposed missions on the horizon. One concept, Persephone, aims to study multiple Kuiper Belt objects, while another, the Interstellar Probe, proposes to venture beyond the Kuiper Belt itself. Specialized orbital platforms are also in development to enhance our capacity to detect and study distant objects. However, these missions will require major technological advances. Propulsion systems, for example, may include nuclear propulsion concepts, solar sails, and ion engines for extended operations. Power sources will need to advance, with next-generation radioisotope generators, more efficient solar panels, and improved battery technologies essential for extended mission lifespans. Communications will also evolve, with optical systems, high-gain antennas, and improved data compression technologies leading the way. Instrumentation will continue to develop, with more sensitive imaging systems, advanced spectrometers, and better radiation-hardened electronics, enhancing our ability to capture and process data from afar. Looking ahead, future Kuiper Belt exploration will likely involve multiple spacecraft working in coordination, sample return missions, and potential orbital platforms around larger Kuiper Belt objects. These missions might even include long-term automated observation stations. However, achieving these goals will require international collaboration and significant technological advancement. Yet, the scientific rewards are immense. We stand to gain a deeper understanding of the solar system's formation, insight into the distribution of organic compounds across space, and perhaps even the discovery of new dwarf planets and other critical objects that could reshape our understanding of our cosmic neighborhood. If this journey to the frozen frontiers of our solar system is freezing your mind with wonder, don't forget to hit that like button. Your support helps us continue exploring these cosmic frontiers with you. And remember, we're just scratching the surface of what's out there in the Kuiper Belt. Each like helps us reach more space enthusiasts like you who share our passion for unraveling the mysteries of our cosmic neighborhood. The exploration of the Kuiper Belt represents not just a scientific endeavor, but a testament to human ingenuity and our relentless drive to push the boundaries of what's possible. As we continue to develop new technologies and launch more ambitious missions, we're not just exploring distant worlds. We're writing the next chapter in humanity's greatest adventure, the exploration of space. The relationship between the Kuiper Belt and comets represents one of the most fascinating connections in our solar system, offering crucial insights into the distribution of fundamental materials throughout space. The Kuiper Belt serves as a primary source of short-period comets, those that complete their orbits in less than 200 years. These cosmic wanderers originate when gravitational interactions or collisions disturb the orbits of Kuiper Belt objects, sending them toward the inner solar system. Short-period comets, grouped into two main categories, exhibit distinct orbits and cycles that reveal a fascinating connection to their origins in the Kuiper Belt. Jupiter family comets, with orbital periods under 20 years, and Halley-type comets, with orbits ranging from 20 to 200 years, display orbital inclinations of up to 30 degrees to the ecliptic plane. This moderate inclination suggests a clear evolutionary path from the Kuiper Belt to becoming active objects in our cosmic neighborhood. The transformation process for these comets involves several critical steps: an initial displacement from stable orbits, followed by gravitational interactions with giant planets, which gradually modify their orbits until they are pushed into the inner solar system, where cometary activity is triggered by increased solar heating. Studying Kuiper Belt objects provides essential insights into comet formation and evolution, offering a glimpse into materials preserved since the early solar system. These objects retain primitive compositions of ice, rock, and dust particles, as well as unprocessed organic compounds, serving as repositories of chemical signatures from the solar nebula. Evolutionary processes include surface modification by cosmic rays, minor impacts, and thermal processing at varying distances from the Sun, inducing chemical changes as objects pass through different orbital environments. The physical characteristics of these comets, such as internal structure, surface composition, and density, reveal important clues about the distribution of water and organic compounds in our solar system. The Kuiper Belt is fundamental to understanding the presence and dissemination of water and organic materials, as comets originating there carry vast quantities of water ice, often delivering it to inner planets. This distribution may have influenced Earth's oceans and even created temporary atmospheres around other bodies. In addition to water, comets transport complex carbon-based molecules, including amino acids and other prebiotic compounds. Cometary activity facilitates the continuous distribution of these materials, while chemical processing in space transforms simple molecules into complex and prebiotic compounds with the potential to be incorporated into forming planetary systems. The impact of these materials on planetary surfaces contributes to the composition of the asteroid belt, regularly modifying planetary geology and potentially playing an important role in creating conditions favorable for life. Today, comet research is focused on analyzing the chemical composition of these objects, studying formation processes, and investigating material delivery mechanisms into the inner solar system. Research on impact frequency and planetary protection strategies proves crucial for understanding our solar system and planetary systems beyond our own. The relationship between the Kuiper Belt and comets represents a vital link in unraveling our solar system's dynamics, tracing the movement of fundamental materials across vast distances and timescales, and helping us piece together the complex story of our cosmic neighborhood's evolution. In the furthest reaches of our solar system, where sunlight barely reaches and mysteries abound, scientists continue to grapple with some of the most intriguing questions in modern astronomy. These debates and mysteries not only challenge our understanding, but also drive us to explore further into the cosmic unknown. The story of dwarf planets represents one of the most heated debates in astronomical history. In 2006, the International Astronomical Union faced an unprecedented challenge. The discovery of numerous large objects in the Kuiper Belt, some rivaling Pluto in size, forced astronomers to confront a difficult question. What exactly makes a planet a planet? The debate that followed would reshape our understanding of our solar system's architecture. The IU's decision to create a new category of dwarf planets sent shockwaves through the scientific community and public consciousness. Under the new definition, a planet must clear its orbital neighborhood of other objects. This requirement meant that Pluto, along with several other large bodies in the Kuiper Belt, would be reclassified as dwarf planets. The decision remains controversial to this day, with some scientists arguing that the definition is too restrictive and fails to capture the complexity of planetary bodies. Perhaps even more intriguing is the mystery of Planet 9. Deep in the outer solar system, something strange is happening. Several Kuiper Belt objects show unusual orbital patterns that seem to defy explanation. These objects appear to be clustered in a way that suggests they're being shepherded by the gravity of an unseen world. This observation led astronomers to propose the existence of a massive planet, potentially 10 times Earth's mass, lurking in the distant reaches of our solar system. The hunt for Planet 9 has become one of modern astronomy's most compelling quests. If it exists, this mysterious world would be about 20 times farther from the Sun than Neptune, making it incredibly difficult to detect with current technology. The planet's proposed orbit would take it through some of the darkest regions of our solar system, where it would receive so little sunlight that even large telescopes struggle to spot it. The orbital anomalies that suggest Planet 9's existence are themselves subjects of intense study. Some Kuiper Belt objects travel in highly elongated orbits that are tilted away from the plane where most planets orbit. Even more mysteriously, these orbits appear to be aligned in ways that seem unlikely to occur by chance. While Planet 9 offers one possible explanation, other theories suggest these patterns might result from the combined gravitational effects of many smaller objects, or even the subtle influence of passing stars. Another puzzling aspect of the Kuiper Belt involves the sharp outer edge of its classical belt region. Known as the Kuiper Cliff, this sudden drop-off in the number of objects beyond about 50 astronomical units from the Sun defies simple explanations. Some scientists propose this edge might have been carved out by ancient gravitational interactions, perhaps from a passing star or even Planet 9 itself. We also see unexplained color variations among Kuiper Belt objects. Some appear remarkably red, while others show neutral colors. These differences might reflect their formation conditions or subsequent evolution, but the full story remains unclear. Each new discovery seems to add another layer of complexity to our understanding of this region. Recent observations have revealed unexpected binary systems within the Kuiper Belt, where two objects orbit each other while traveling around the Sun. The frequency of these binary systems challenges our models of planetary formation and evolution. How did these pairs form? Why are they so common in this region of space? These questions continue to puzzle astronomers. The mysteries of the Kuiper Belt remind us that even in our own cosmic backyard, significant discoveries await. Each unexplained phenomenon provides an opportunity for new theories, new observations, and potentially paradigm-shifting discoveries. As our technology advances and our understanding grows, we move closer to unraveling these cosmic riddles, while undoubtedly discovering new ones along the way. In the end, these mysteries and debates serve a crucial purpose in science. They drive innovation, spark curiosity, and remind us that the universe still holds countless secrets waiting to be discovered. As we continue to study the Kuiper Belt and its enigmatic inhabitants, we're not just exploring the outer solar system, we're pushing the boundaries of human knowledge itself. Beyond the familiar boundaries of our planetary neighborhood lies a cosmic wilderness that challenges our understanding of where our solar system truly ends. The Kuiper Belt serves as a gateway to even more distant frontiers, offering profound insights into the structure of our cosmic home and other planetary systems throughout the galaxy. The relationship between the Kuiper Belt and the Oort cloud represents one of the most fascinating connections in our solar system's architecture. While the Kuiper Belt forms a relatively flat disk beyond Neptune, the Oort cloud exists as a vast spherical shell of icy bodies extending nearly halfway to the nearest star. These two regions, though distinct, tell a connected story of our solar system's evolution. The transition zone between these regions holds particular interest for astronomers. As we move outward from the Kuiper Belt, we encounter the scattered disk, where objects follow more elongated and tilted orbits. These scattered objects appear to form a bridge between the relatively ordered realm of the Kuiper Belt and the chaos of the Oort cloud. Their orbits suggest a dynamic history of gravitational interactions, possibly caused by ancient encounters with passing stars or the migration of giant planets. What makes this connection especially intriguing is the origin story it reveals. Both regions likely formed from the same primordial disk of material that created our planets. However, while the Kuiper Belt retained its disk-like structure, the objects that would become the Oort cloud were scattered outward by the gravitational influences of the giant planets. Some were ejected entirely from the solar system, while others settled into distant orbits, forming the spherical shell we now call the Oort cloud. The study of the Kuiper Belt has revolutionized our understanding of other planetary systems. As we discover disks of debris around other stars, the lessons learned from our own Kuiper Belt provide crucial context. These distant disks often show structures and compositions remarkably similar to our Kuiper Belt, suggesting that the processes that shaped our solar system may be common throughout the galaxy. Particularly illuminating is how the Kuiper Belt's structure reflects the gravitational choreography of planet formation. The various orbital resonances, gaps, and clusters we observe help validate our models of how planetary systems evolve. When we spot similar patterns in extrasolar debris disks, we can apply these lessons to understand their histories and potential planetary systems. The Kuiper Belt also serves as a natural laboratory for studying the building blocks of planetary systems. The preserved primitive materials we find there provide insights into the composition of the protoplanetary disk from which our planets formed. This information proves invaluable when analyzing the chemical signatures we detect in other stellar systems, helping us understand the conditions necessary for planet formation throughout the galaxy. Perhaps most profoundly, the Kuiper Belt challenges our traditional concept of our solar system's boundaries. The classical view of our cosmic neighborhood, ending neatly at Neptune or Pluto, has given way to a more nuanced understanding. We now see our solar system as a complex, layered structure extending far beyond the planets, with each region telling part of our cosmic story. The gradual transition from the Kuiper Belt to the scattered disk, and eventually to the Oort cloud, suggests that our solar system doesn't have a clear edge. Instead, it slowly fades into interstellar space, with the influence of our sun's gravity gradually diminishing. This understanding has important implications for how we define planetary systems and their spheres of influence. Recent discoveries of distant objects like Oumuamua and various interstellar comets have further complicated our understanding of these boundaries. These visitors from other star systems remind us that our solar system isn't isolated, but exists in a dynamic galactic environment. The Kuiper Belt likely interacts with similar regions around other stars, participating in a cosmic exchange that has continued for billions of years. The Kuiper Belt's relationship with these outer regions also raises intriguing questions about the origins of life. The complex organic compounds found in Kuiper Belt objects suggest that the basic ingredients for life might be common in the outer reaches of planetary systems. This raises the possibility that similar regions around other stars could also harbor these crucial biological building blocks. Looking to the future, Our exploration of the Kuiper Belt and beyond continues to yield surprises. Each new discovery forces us to revise our models and expand our understanding of cosmic architecture. As we push the boundaries of our observations further into space, the lessons learned from the Kuiper Belt guide us in understanding not just our own cosmic backyard, but the fundamental processes that shape planetary systems throughout the universe. The story of the Kuiper Belt and its connection to more distant regions reminds us that our solar system is far more extensive and complex than we once imagined. It stands as a testament to the dynamic nature of cosmic systems and their interconnectedness across vast distances of space and time. As we continue to explore these frontier regions, we're not just mapping our solar system's outer reaches. We're uncovering the universal principles that govern the formation and evolution of planetary systems throughout the cosmos. When we gaze into the dark expanse beyond Neptune, we're not just looking at a collection of distant, frozen worlds. We're peering into a cosmic time capsule that holds the secrets of our origins. The Kuiper Belt stands as a testament to the incredible complexity and beauty of our solar system, challenging our assumptions and expanding our cosmic perspective in ways we never imagined. This remote region serves as nature's own astronomical archive, preserving the primitive materials and conditions that existed during our solar system's infancy. Each icy body orbiting in this distant realm tells part of our origin story, carrying chemical signatures and physical features that date back to the very beginning of our planetary neighborhood. By studying these ancient objects, we're essentially reading the first chapters of Earth's cosmic biography. The discovery and ongoing exploration of the Kuiper Belt represents one of humanity's greatest scientific achievements. It reminds us that even in an age of interplanetary missions and powerful telescopes, our own cosmic backyard still holds profound mysteries waiting to be uncovered. Each new finding from this region has forced us to revise our understanding of planetary formation, orbital dynamics, and the very nature of our solar system's architecture. But perhaps the most compelling aspect of Kuiper Belt research is its potential to answer fundamental questions about our place in the universe. How common are planetary systems like ours? What role do outer solar system regions play in the potential development of life? These questions reach beyond mere scientific curiosity. They touch upon our deepest wonderings about existence itself. The future of Kuiper Belt exploration holds enormous promise. As our technology advances and our methods of observation improve, we stand on the brink of even more remarkable discoveries. Each new mission, each new telescope, and each new analysis technique brings us closer to understanding not just this particular region, but the fundamental processes that shape planetary systems throughout the galaxy. Our journey through the Kuiper Belt teaches us an important lesson about scientific discovery. The universe is often more complex and more fascinating than we initially imagine. What began as a theoretical prediction has evolved into a rich field of study that continues to surprise and inspire us. It shows us that the frontiers of knowledge are not fixed. They expand with each question we dare to ask and each observation we manage to make. This frozen realm beyond Neptune serves as a bridge between our familiar planetary neighborhood and the vast wilderness of interstellar space. It reminds us that our solar system doesn't end abruptly at Neptune's orbit, but gradually transitions into the broader galaxy through layers of increasing complexity and mystery. Understanding these transition zones is crucial for comprehending our place in the larger cosmic context. If this journey through the frozen frontiers of our solar system has ignited your passion for cosmic exploration, your adventure doesn't need to end here. There's so much more to discover about our fascinating universe, and we're here to guide you through every astronomical wonder. Join our community of cosmic explorers by subscribing to Exploring the Universe. Every week, we venture into different corners of the cosmos, unraveling the mysteries that make our universe such an incredible place. Whether it's diving into the storms of Jupiter, sailing through Saturn's rings, or exploring distant galaxies, there's always something new to discover. Hit that subscribe button to ensure you never miss our latest astronomical adventures. Give this video a thumbs up if you've learned something new about the Kuiper Belt today, and share it with fellow space enthusiasts who might be fascinated by these frozen worlds beyond Neptune. Drop a comment below sharing what aspect of the Kuiper Belt you find most intriguing. Maybe it's the mysterious Planet 9, the reclassification of Pluto, or the possibility of hidden oceans on distant dwarf planets. Your thoughts and questions fuel our cosmic conversations and inspire future explorations. Remember, Every time we look up at the night sky or peer through a telescope at distant worlds, we're participating in humanity's greatest adventure, the quest to understand our place in the cosmos. Together, let's keep pushing the boundaries of knowledge and exploration. This is Exploring the Universe, where every video is a new journey through the wonders of space. Until our next cosmic adventure, keep looking up and wondering about the magnificent universe we call home.